Hello. Hello, everyone. Can you hear me? Okay, please turn on your camera. All right. Today we have a lot of things to do, so let's get started. So today we are going to finish the object detection part, and we are going to study about the segmentation. So sorry, this is not. Yes. So as a reminder, in the next Monday we are going to have the midterm exam in the same time as we have the class. And it will be offline, so you have to come to the classroom, which is building 942, rooms 301 and 302. You guys will be split into two different rooms. And if you have any reason that you cannot come physically, please let us know as soon as possible so that we can adjust the time or location or that should be just exceptional. If you have any strong reason to do so, please let us know that we can admit some different alternative way of doing the exam. Other than that, you have to come to this office, the lecture room, and the coverage will be until what we covered today. So everything we have covered so far will be included in the exam. And the reading materials and the papers linked on the website, the course website, will be included. But the papers only linked in the lecture notes will not be directly asked, as I told you. And I also posted that I have these lecture recordings publicly available until the midterm in this website. So you can always take advantage of these videos to review the materials and prepare the exam. And also, about 1 or 2 hours ago, I posted the previous exam. So I taught this course, the same course in the last spring semester, and I posted the midterm exam from the last semester. So you can use that to understand what is the style of the questions. And it will be kind of similar style in this time too. Okay? Any question? Okay. So let's quickly review what we've done last time. Okay. Song Jisoo?
Professor?
Yes. What is the object detection problem?
Well, sorry, I didn't really understand your question.
So can you formally define what is object detection problem or task?
It's kind of finding the ROI which contains the desired object and classifies which is which.
Mm-hmm. Yes, exactly. So in object detection problem, we like to detect all the instances of a set of classes that we already predefined. And we have to find all of those instances in the image and need to locate them where it is in the form of the bounding box. So great job, Jisoo. And next question to Soyeon, Park Soyeon. Okay, we covered two-stage method and one-stage method last time. And in the two-stage method, the oldest one was the RCNN. And after that, they have a faster version of that, which is fast RCNN. So what was the main idea there? Soya, can you hear me? Sorry, Soyeon. It's too noisy. Sorry. Sorry, let me ask to someone else because it's too noisy and everyone is kind of suffering from the noise. Okay. Okay. Then Ho-in. Jong Ho-in.
Yeah.
Yeah. Okay. So what was the main idea of fast RCNN from the original RCNN?
Well, actually, I couldn't recognize what is the difference from fast RCNN and faster RCNN. So
Oh, no. Not, what I'm asking is not fast versus faster. I'm asking the regular RCNN and fast RCNN, the very first two.
I think they change it in faster RCNN. They change it the way to extract the feature by using hierarchical architecture. Actually, I'm not sure about this. I couldn't study, and I couldn't spend much more time.
Okay, yeah, that's okay. Let me ask someone else. Jungursen, you're muted.
Can you hear me?
Yes.
Okay, perfect. So the difference between RCNN and fast RCNN is that instead of passing like all the spatial parts of the input image through the CNN, you only pass like the input image and then use the spatial areas of the feature map of the output of the CNN.
Yeah, perfect. So they introduced ROI pooling, region of interest pooling, so that they can just feed the entire image once to this convnet, and they use the convolutional feature map from that model and apply the ROI pooling to represent each image patches. So that was the main idea of the fast RCNN. And you may expect my next question. So let me ask it to Jayon, Yu Jayon.
Yes.
Yes. What is the main idea of faster RCNN from fast RCNN?
The difference is generating proposals. In faster RCNN, RPN is trained to generate proposals for images.
Great job. So yeah, until fast RCNN, they used off-the-shelf region proposer methods like selective search, which is super slow. And they introduced the region proposer network, or RPN, within the network, so they can train everything within the entire network. So great. And the last question is okay, to Daniel. Daniel Kim. I'm not sure who you are. Probably you have a Korean name, but you're not answering. Okay. Okay, let's ask to Thomas.
Yes.
Yes. What was the main idea of RFCN?
Yeah, that's a good question. Let me think. Yeah, I'm sorry, I'm not really completely sure. It's an extra. Well, I remember that it's built on after the as a faster RCNN, but I'm not completely sure. Oh, well, I think
it has something to do with the at the end of the convolution or something. So each ROI is mapped to. Yeah, I'm
It's
sorry
okay.
that I'm
It's okay.
confused.
Yeah, you don't have to. Sorry, just please review that before the exam.
Yes.
Okay. Okay. Who else? 서영? 이서영?
Yep.
Yeah. What is the main idea of RFCN?
The main point was that we use features that are position sensitive, so we can consider the orientation of the objects. So, yeah.
Yeah, great. So the main difference between the RCNN or its faster versions versus RFCN is the multiple channels we train is position specific. So we train the features or representations optimized only for some specific part within the bounding box. It's top left or top right or top center, something like that. So that was the main difference of the RFCN, and they improved the performance a little bit of the detection. So, okay, so everyone, good job. And please review if you are not familiar with the questions I asked, because those are the really basic main ideas that we have discussed in the last lecture. Okay. Okay, today we're going to finish the this part with SSD, the very last model we are going to learn in the detection. So SSD stands for single shot multi-box detector. So similar to YOLO, this is also single shot model. So we don't do this two stages, which is the region proposal first and then classify them. But here we do everything at once. So, so the main idea is, given the input image, which is 300 by 300 here, they first extract the features using some existing pre-trained ConvNet, which is VGG16. Sorry, it may not be pre-trained, but they just initialized using the VGG, but they probably fine-tuned this as well. So from the VGG16, they have conv1 to conv5, as you may remember from our lecture 8. So they are embedded into the conv features. And then they stack additional conv layers. So here you see very small letters, conv6, conv7, instead of fully connected 6 or 7, and conv8, and conv9, and conv10. So they stack more layers on top of the VGG network. And each of them, you see that the size gets even smaller from 38. They become 19, and here 10, and 5, 3, and eventually 1. So instead of using the fully connected networks, they apply multiple level of additional conv layers to reduce the size half and half again and again until they have 1 by 1, the finer embedding. So why do that? So here you see that we would like to detect these two dogs, and one of them is larger and the other is smaller. And our goal with the detection task is that we would like to locate whatever the target object, and regardless of their size. So our detector should be able to detect small objects as well as large objects with a single model. So in the in the earlier stage after this VGG, they tend to finer grade to represent the entire image. So here, for example, this is 10 by 10. So they apply 3 by 3 patch everywhere after that. So if they, when we apply 3 by 3 conv on 38 by 38, then those 3 by 3 will represent very small region of the network. But if we apply that here, 5 by 5, for example, then that will cover very large space. So that's how they detect a small object and the large object at the same time. So in the earlier feature maps, they conv with 3 by 3 on 10 by 10 like this. Then we'd like to find out these objects of this target size here. But in the next layer, for example, 5 by 5, the 3 by 3 will cover a very large area within this entire image. So this is optimized for detecting the larger images. And they concatenate all of these conv features from conv 5, 6 to 11 here. And they actually detect all the classes using all of these multiple sized features. So the key idea is using the same size of conv filter, which is 3 by 3, but they operate on different scale of the conv features from after the conv 5, and they should be able to detect whatever the size it is using the targeted features with the proper size. So that's the main idea of SSD. And the loss functions is actually very similar to what we've done with YOLO. So basically, it's actually similar to the previous one too, the faster RCNN. Basically, they do the conf here. It means the classification confidence, and loc means this localization part. So as a reminder, we are doing the detection, which is classification plus localization. So for the classification part, they use the loss function looks like the cross entropy. So here, this is the class-specific score from their model, and it is multiplied with the ground truth scores. And so they wanted to maximize the predicted score for the correct class. So this was the definition of the cross entropy for the classification task. And here they add one more term here. So I is the index of the image, and if that's belonging to the negative, which means that particular detection part is nothing. It's not an object to detect, but it's just a background. So if that belongs to nothing, then we have to maximize the score for the background or none. You may remember that in our previous examples, we have seen that the classification, we have all the classes, and then we had a none. So this is that part. We have to maximize the score for the none if we actually don't have the objects in the ground truth in that region. So this is the classification confidence part. And for the localization, this is almost the same as what we've done before we discussed. So they use the smooth L1 loss between this localization and the ground truth. And each of these are very similar to what we've done. The target, you may remember that from the model, we have the estimation, then have the target values, and they apply the regression, do you remember? There, they used L2 loss, but here they used L1 loss. That's the only difference. But philosophically, they are basically the same. So this is the loss function for SSD, and it is important to understand what they are trying to do here. And if you can read and understand what these complex formulas are doing, then you can say that you can understood. So this is their results on various data sets. So here, the SSD achieved the best scores compared to like fast RCNN, faster RCNN, or they probably have compared to YOLO here. So performance-wise, accuracy was the best with using the SSD, even better than the faster RCNN, which is great actually, because this is the one-stage method, but faster RCNN was two-stage, which is expected to be performing better. Otherwise, we don't have any reason to do the two-stage things. So they achieved even better accuracy on this data set. But speed-wise, actually, the SSD was better than the faster RCNN, a lot more faster, but it is slower than YOLO. So YOLO is less accurate, but it's much faster because they intended to be real-time. So it's their conclusion about the experiments. And after that, a lot of proposer-free approaches were also proposed. And some of them are like YOLO version 2, 3, and 4. And some other variation of the SSD. So recently they are still continue to publish the papers for the this task. So if you're interested in, you can feel free to read it. But as I told, these kind of additional papers are not a part of the midterm. But if you do some research on this or interested in this, I strongly encourage you to refer to these papers. So this is the end of lecture 9, and I'd like to give you the time for questions, but because we have a lot of things to do today, let me get the questions at the end of today's lecture.